Hello, my name is Avon, and this is my CPU emulator project that I created. So essentially what it is it is a program that emulates this 8-bit processor, which is the MOS 6502. And it's an 8-bit processor from the 1970s, and it was used in some pretty famous computers slash gaming consoles like the NES by Nintendo, the Apple II, and the Commodore 64. And it has a couple registers, but only three main ones, which are the accumulator, which is used for like addition and all that stuff, and then just an X and Y register, which is typically used for indexing. And it has 151 official opcodes, which are each 1 byte, and these opcodes covers 56 different mnemonics or functions, such as like loading into the accumulator, storing something, etc., etc. And my implementation has a 64 kilobyte, I guess you could call it RAM, but it's also split up in a way that half of it is ROM, the higher half is the read-only memory for the program, and it also has a 256 byte stack like a standard 6502, and the same thing applies for the zero page. And so this CPU and this architecture is responsible for the home computer revolution, which is why it's an interesting choice to emulate, and which is it's why I chose this as my project. So what I built is a fully working 6502 emulator in C++, and essentially the whole gist of it is that you could take a compiled binary for the 6502 with the 6502 assembly. You could use any assembler, like I used CA65, and you can compile it, and you should be able to run it through my emulator. And so that's what I was able to achieve within the scope of this project. And so all official opcodes are supported, minus decimal mode, because it's slightly finicky and it's not used that much, at least for most standard programs. And so my emulator implemented correct flag behavior, so like the P flag, it has all the negative overflow carry, and like the B flag, all that stuff, etc. As well as like stack operations and memory operations, like storing, loading, stuff like that. And I verified it with a special suite of test cases using Catch2, which is a C++ testing framework. And the test cases that I used were created by Tom Harte, who created a suite of tests called processor tests, which are basically built for emulators. And there are a bunch of JSON test cases, which I just plugged into Catch2, and then I was able to incrementally test my instructions and opcodes, and yeah. So I'm going to quickly demo my 6502 project and show it around a bit. So to start off, we have a couple structs in our components.h file. So obviously we have the CPU, and so here we have our equals operator. This is used for testing. We have a toString function, which I use for debugging every now and then. And so we have a couple registers, like a program counter to keep track of like the opcode that's currently being executed, the accumulator for arithmetic and all those types of operations, and then general purpose registers. And then the stack, one of the interesting things was that the stack grows downwards on these machines, which is something that I did not anticipate, so that was quite interesting to know about. And also the processor state, which is used by 6502 to, I guess, add extra information about certain operations, like if you add, if it overflows, something like that. And then we have our memory. Our memory is just standard 60-something kilobyte memory, and it has like a small stack, it has some defined regions, etc., etc. All these are thrown or strung together in this MOS 6502 header file, and essentially start off we have our address modes, because the 6502 has many modes of addressing that we can use to access memory, and this was quite a challenge to implement, as we'll talk about later. And then also we have our instruction struct, and basically just represents like what an instruction is. It provides details about the instructions, and so that's that. And then we have our emulator struct, which is just combining these two components here and implementing the actual instructions And so as you can see here, we've implemented all of our 6502 standard instructions, such as LDA, LDX, LDY, load into accumulator, and stuff like that, and then like transferring, incrementing, decrementing, interrupt related, and all of these special little things. So that is how this is built. And then for the test cases, I created a simple class called hardatest.h, which is a simple class. It has like the JSON for the test case, and it has an emulator for the initial state and an emulator for the final state. And so we load in our test bench here, and then we load in the expected values here, and we just run the test case over here, and it returns a bool if it fails. And it does many assertions on like the register states, and it makes sure that certain memory addresses are valid, because in the hardatest, which I can show here, they have basically a bunch of little JSON files, and it has like expected register values and expected RAM values. It also has like cycle stuff, but I didn't really check for this because I was mostly going for functionality and not cycle accuracy. So those are the test cases. And so now to demo this, essentially what you can do with my emulator is, so I have an ASM folder here, and so this is a simple 6502 assembly file. This is how it would be written in the 70s. It's how it's written now, and you can assemble it using this make file, which I've already done here, or I can actually do that right now. So I can go, so I can just run make, and there I have my basic assembly file for the 6502. So if I do this onto a real one, it should run just as it runs on my emulator. So I'm just going to rename this to test.bin. And so what this file does, just for those that want to know, is that it clears the decimal mode, it clears the carry, and it loads 5 into the accumulator, and it adds 3 to it, and then it just halts the program. So yeah, so the expected result is that you should have 8 in the accumulator, and we will see that happening in a moment. So I'm just going to go back here. I'm going to go to my build file. I'm just going to build my emulator, make sure everything is built properly. So as you can see, it's passing, don't mind that. And I am going to run my emulator. And so now it's asking us to enter our binary file, which I named to test.bin. So as you can see, it runs our code. As you can see, the program counter got incremented by 7 bytes, which means that it's running something. And the accumulator starts at 0 but ends up at 8, just as the assembly file intended with this LDA ADC operation. And also our processor has updated accordingly its status flags as well. So that's how it works, I guess you could say. And so it's pretty cool. And regarding the accuracy of the emulator itself, it is rigged with C-test, and so VS Code has a built-in tool, I guess, for helping C-test become a more easier interface. So as you can see, I can like run certain tests. So this is testing the jump to subroutine opcode, and so it runs a specific test case, and as you can see, it's passing. And the reason it's passing is through this implementation here. I have a get test cases function that extracts the test cases, and then also I have a run hardatest function which runs it on that specific case or opcode, and then they're all just declared here. So in that case, in the case that we just ran, which is jump to subroutine, it's implemented right here, 20 absolute, 20.json, and so it plugs in everything together, and overall makes it pretty solid and reliable as a 6502 emulator. And then some of the challenges that were found in the creation of this emulator. It was quite an interesting project, but it came with many challenges. So first off, there was like off by one edge cases, such as like the program counter or the stack pointer being off, especially when you're implementing like certain instructions such as jump to subroutine or certain stack operations or like return to interrupt or break. These instructions, you need your program counter to be in the specific location. And the way that I designed my emulator was slightly non-standard in the way that it incremented the program counter, so it took a little bit of debugging to sort of, find like the exact location that things should be at. So as you can see, like I have a -1 here. Originally it was not like that, and like these +1s, these were things that took a lot of time to sort of figure out and debug. Um, Also the address modes, to be honest, I still don't know how they work kind of, and so they're quite hard to wrap your head around and like exactly why you would need them, especially like the indirect index and indexed indirect. Those are pretty easy to confuse, and also like the idea that a zero page exists was kind of hard to wrap my head around, but it makes sense now. So those are some things that were quite interesting. Also, the processor's status register was quite an interesting thing to learn about and implement, because even though like it has the negative or like the zero or the overflow or carry flag, these can often mean different things in different contexts. So for example, if I'm in the compare instruction, just need to go here. Yeah, so um, you would expect the zero flag to be set when something is zero, but in this case, the creators of the 6502 decided that in order to indicate an equality of values, that they should set the zero flag if it's equal. So those are things that are like kind of hard to wrap your head around. And also overflow calculations, they result in pretty cryptic code. So like for ADC and SBC, let's go here. Yeah, so to calculate overflow, this bit banging is quite a goofy or like unusual thing that honestly I still don't understand. It's quite cryptic, but it works, so we'll just go with it, I guess. Um, Also, addition and subtraction, implementing them is supposedly one of the hardest things on the 6502, according to many people. And their implementation is slightly weird because of the way that the carry flag works. And so it took me a while to wrap this around my head, but the whole point of like the carry flag is that it's supposed to help with 16-bit addition and subtraction. And so that took a bit of time to wrap my head around, and also like the way that it's implemented is slightly unusual. So like as you can see here, it's a interesting formula for subtraction. It's not as straightforward as you would think it would be. So that was definitely something that I guess challenged me. Also, debugging. Yeah, reading hexadecimal is kind of hard if you haven't really read hexadecimal. So I kind of got used to that, so at the end it was a little easier. Also, it's kind of hard to debug without any visuals. Like if it's a game, you'd be able to see like what's happening or what's going wrong, but it's just internals and like very niche things that could go wrong, or like maybe something's off by one, like I said earlier. So debugging those is pretty hard, and also like when the test cases were being ran, it can be quite difficult to understand what exactly is going wrong, because these test cases are relatively unreadable. They're compacted, like one case per line. So using AI definitely helped with understanding what the test case was intending, and I was even able to find that one test case was invalid. So things like that, reading these is quite difficult, but we got over it and now everything works. And also clean code. It was kind of hard to keep the code clean, as you can see here. This is the instruction map binding for our opcode lookup table. It is quite long and it's not clean at all. And also like making it readable, like especially with the overflow calculations or like, your memory operations. So things like that. And also like overflow bugs because the 6502 has a maximum register size of 16 bits, but it typically is 8 bits depending on which registers you're talking about. And so simulating that wraparound if the value overflows was something that confused me a little bit. And so, um, but after I got my head around the idea, it was pretty simple to fix. You just need to cast to word and it will cut off and wrap around. Or you need to cast to byte and it'll do the same thing. So those were a little difficult to debug. And also hardware glitches. So like the 6502 has certain like hardware bugs such as like the page crossing bug, which is found the indirect um in the indirect memory access mode. So basically with this thing, it's like if you cross a page, which means like the upper 2 bytes of your address have moved, um, that basically means that the indirect would wrap around. I believe it was something like that. Yeah, so just like it would like wrap around to the beginning of the page essentially instead of going to the next page. So it was kind of weird in that sense, I guess, to implement. So yeah, like hardware glitches, they were cool to learn about, but overall, a little bit of a pain to write. As you can see, this code is pretty cryptic. It's a bunch of bit banging to check if it like crossed the upper bytes, and then it wraps around accordingly. And yeah, so those are some of the challenges with implementing the 6502's, I guess you could say, like instruction set and architecture and like bugs and all those things. So overall, it was a pretty good project. I learned how CPUs work. I learned a little bit about assembly and how it's written and what it does. And I learned how machines represent their code. It's actually a lot simpler than I thought. And it's not just ones and zeros. It's more like numbers that represent certain operations. And also, I learned about the function and usage of registers. And this was an idea that didn't really get to me until I implemented this project. And then like the accumulator or the X or the Y register, like how they're used. And also I learned about how to write unit tests. So Catch 2 was pretty useful for this, and it's a great software engineering practice. So I guess that's pretty useful. And also a lot about computer bugs and glitches like overflow, page crossing, page penalty, such as like incurring extra cycles, things like that, just from reading and like implementing. So yeah, and so that's it. Might as well do another project now. Thank you for watching.